An incoming webhook payload is an aggressive, highly untrusted entity. It hits your internal server environment completely blind. To handle this traffic safely, we need to architect the HTTP API for Webhook Relay, our reliable webhook delivery microservice. Our strict constraint for this build is that the entire system will rely purely on Go 1.22's native capabilities. There is a common assumption among engineers that building a production-grade application in Go requires heavy third-party web frameworks like Gin or Echo to handle the routing complexity. That is no longer true. In a production environment, the API functions as a layered perimeter defense system. This defense relies on three structural pillars: sequentially quartered middleware, strict payload validation, and consistent response contracts. The primary function of this API is to aggressively filter, sanitize, and validate every incoming request before it ever gets the chance to touch the core business logic. This 2D schematic shows a data packet arriving at the outermost layer of our system pipeline, the Go 122 servlux. The native router directs traffic strictly based on HTTP methods. It routes a POST request directly to the create event handler. Conversely, when a GET request hits the router, it travels down an entirely separate path to the list deliveries handler. Go 122 introduces powerful native pattern matching capabilities for dynamic URLs. Notice how the path includes a distinct ID segment. The router extracts these path parameters automatically, isolating variables directly from the URL string so they can be consumed by downstream processes. Historically, isolating these variables in Go meant importing heavy third-party regex libraries to parse the request strings. Using native method-based routing eliminates that dependency bloat while maintaining strict typing and high execution speed. Moving out of the router, this animated diagram tracks the request entering a sequential execution pipeline marked by 5 distinct gates. This is the middleware chain. Each request must pass through these execution gates in a specific sequential order before reaching the handler. At the first gate, the system checks for an existing X-request ID header from the client. If none exists, it generates a fresh one and stamps it onto the payload. Placing this ID generation first guarantees end-to-end traceability across the entire lifespan of the microservice execution. Next, the request reaches the second gate, logging. Here, the system instantiates a request-scoped slog logger. It injects the newly created request ID, the HTTP method, and the path, ensuring all subsequent actions share this exact context. The third gate acts as a containment field for panic recovery. This specific middleware layer wraps the execution of all downstream logic, standing by to catch any fatal panics triggered by unexpected business logic errors. Instead of allowing a bad request to crash the entire Go daemon, this layer catches the panic, logs the full stack trace via slog, and returns a clean HTTP 500 error to the client. Together, these first 3 gates establish our observability and stability perimeter, successfully isolating infrastructural failures from application code bugs. With the payload stabilized and tracked, it advances deeper into the pipeline toward the inner gates. The fourth gate is authentication. This barrier validates the API key provided in the HTTP headers and extracts the unique tenant ID associated with that specific key. Unauthorized or malformed requests are dropped instantly, returning an HTTP 401. Rejecting bad traffic here saves valuable compute cycles downstream. The surviving packet then arrives at the final defensive gate, rate limiting. The system feeds the previously extracted tenant ID into an in-memory rate limiter. If a tenant pushes abusive or runaway traffic, the gate issues an HTTP 429 and halts the flow. As we noted in Season 1, in-memory limiters are node local and not fully distributed across a cluster. However, they provide a highly performant, sufficient baseline for this phase of the build. These inner gates protect downstream database resources, maintaining strict data boundaries against both noisy neighbors and malicious actors alike. The packet clears the middleware and enters the innermost core of the system, the scanning bay for the create event handler, exposing its raw JSON payload. This stage is built on a single premise: never trust client input. Before a single byte of data is written to disk or placed onto an asynchronous queue, the JSON payload must be structurally and semantically validated against rigid rules. If a payload is malformed or missing required data, the scanner rejects it immediately, completely halting execution. When this happens, we generate a structured HTTP 400 bad request object. Returning a generic, unhelpful text string creates unnecessary friction. Instead, this structured error response specifies exactly which keys or fields failed validation, providing a clear path to resolution for the client developer integrating with the API. This strict input validation forms the explicit binding contract between the webhook service and anyone consuming it. Once a request is successfully processed, the flow direction reverses, sending two distinct JSON response templates back to the client. To ensure predictable parsing, the API uses a nested data field exclusively for success payloads and an error field solely for failures. Finally, we append HTTP status codes and rate limit headers to every outgoing response. For list endpoints, we implement pagination using cursor-based tokens. This method prevents the severe performance degradation associated with traditional offset pagination when operating at high volume. Designing these predictable, highly structured exits is just as critical to the microservice architecture as building secure entries. The HTTP API shell for Webhook Relay is now fully complete. It is hardened by sequentially ordered middleware and strictly typed via Go 1.22's native capabilities. With this perimeter defense established, we can confidently ingest client data without risking internal system stability. In the next episode, we will take this safely validated data and hand it off to the asynchronous delivery worker for reliable downstream processing.